In Chapter 5, we take up the idea of anti-differentiation or integration, and basically those terms mean the same thing. And so let's start with a definition here. A function capital F, now remember in mathematics is case sensitive, so capital F and little f are different, or lowercase f are different things. A function capital F is called an antiderivative of function f on an interval I if the derivative of capital F is little f. So capital F is an antiderivative of little f if the derivative of capital F is little f. So going from little f to capital F is an antiderivative, and going from capital F to little f is a derivative. Okay, for all x on the interval I. All right. In this case, f is called an antiderivative. It's also called an indefinite integral. Antiderivative and indefinite integral are synonymous. They mean exactly the same things. Okay, so let's take a look at an example. We know the derivative of sine of x is cosine of x. We know the derivative of sine of x is cosine of x. So now here's the notation that we use to talk about an antiderivative. It's this kind of S-looking symbol. This is called an integral sign. All right, and then notice there's kind of a delimiter that starts with the integral sign and it ends with dx. Dx means the variable. It indicates a variable with respect to which you're calculating an antiderivative. Notice in this case we're calculating an antiderivative with respect to x. All right, here we're calculating an antiderivative with respect to x. It just works backwards through the same formula. All right, so the derivative of sine of x is cosine of x. Then the antiderivative with respect to x of cosine of x is sine of x plus c. Now why the c? Why the c? Well, if we look at this, the derivative with respect to x of sine of x is cosine of x. So that means that the integral, I'll leave off the c for right now, going backwards, the integral with respect to x of cosine of x is sine of x. But notice we could also have written the derivative with respect to x of sine of x plus 3, sine of x plus 3 is cosine of x. So it would have made just as much sense to write the antiderivative of cosine of x is equal to sine of x plus 3, because when I take the derivative of sine of x plus 3, I get cosine of x. Similarly, the derivative with respect to x of sine of x, I probably should have put this like this, sx minus 7 is cosine of x. So it would have made, again, as much sense to write this as cosine of x dx is equal to sine of x minus 7. So you see, notice we could have any number we like back here, because any constant in here, right, is just going to be 0. We're going to get 0 when we take its derivative. So when we anti-differentiate, we could get a constant. This is called the constant of integration. When you differentiate, when we look at the derivative, we don't know what constant we've lost, so we have to expect anything. All right, we have to expect anything. All right, but this will be a constant. It can only be a number. Okay. All right, so let's take a look at this. Let me just take a look at one more thing here before we go on. If I took the derivative with respect to t of sine of x, notice what I get. I would get cosine of x times dx dt. Again, we'd have to use the chain rule. We'd have to think of x as a function of t, and we'd be using the chain rule. So notice that this would say that the antiderivative with respect to t of cosine of x, now dx dt, is equal to sine of x plus a constant. Notice what this value, this expression here, tells me what I'm integrating with respect to, and we're working backwards through the formula where we're differentiating with respect to that very same variable. So I want you to keep that in mind. A couple of examples. All right, notice that the derivative with respect to t of natural log of t is 1 over t. So an antiderivative of 1 over t with respect to t is natural log of t plus a constant of integration. Okay, and I guess I could fill these in. I probably should have left these out. But anyway, all right, the next thing I want us to keep in mind is that we have these properties of derivatives, that the derivative of a sum is the sum of the derivatives, derivative of a difference of the derivatives, and so on. All right, basically we have the very same ideas here for antiderivatives. For antiderivatives, they follow these linear properties. All right, the antiderivative of sum, well, we can take the antiderivative separately and then add them when we get done. The antiderivative of difference, we can take the antiderivative separately and then subtract them when we get done. The antiderivative of a constant times a function is the constant times the antiderivative of the function. And the antiderivative of x raised to the r is x to the r plus 1 over r plus 1 plus a constant of integration. Notice we could run into a problem at one place there. If r were negative 1, if r were negative 1, we'd be dividing by 0. So this works for r not negative 1. It works for any other value of r. By the way, the antiderivative, if r is equal to negative 1, we'd be taking the antiderivative of x to the negative 1 dx, which would be the antiderivative of 1 over x dx, and that would be the natural log of x plus c. So anyway, so I just want to point that out. Notice the natural log fills in that gap. All right, that's left with our power rule. Okay, and that's the basic ideas of antidifferentiation. Next videos we'll look at some examples of antidifferentiation.